Welcome to the second part of the MATH1 exam of the 3rd of April 2020. I will continue with exercise 4. So there is a set A and a relation R on that set A. Set A is given with 4 elements, 1, 2, 3, 4. And we have a relation given with an arrow diagram. Question A, give the number of elements of the Cartesian product RR. Well, that is of course quite straightforward. However, there's one trick here in this question. Normally we are used of having a Cartesian product of 2 sets, of one set with itself, so AA for example. But now they're asking a Cartesian product of a relation. Basically it's just the same. Now, if I would ask you the Cartesian product, the number of elements of AA, then you would say that is 4 times 4, huh? Just the number of elements in that set times the number of elements in the same set. But in this case we're looking at a relation, so we have to check how many elements are in the relation. And then we have to count the arrows. So we have 3 arrows, so that means there are 3 ordered pairs in the relation. So the answer, the number of elements in the Cartesian product RR, is the number of elements in the relation times the number of elements in that same relation. So that's 3 times 3, that is 9. And a lot of students just thought, okay, number of elements, Cartesian products, A, 4, 4, 16. By the way, help me to give you some points. So if you would make that mistake, then just say NAA is 4 times 4, then I still know that you know what a Cartesian product is. And then the only mistake you made is that you didn't read the question carefully. And so I'll give you some points for it. Question B, composition relation. So RR. Okay, how do we make a composition relation? And the most simple one is just put the arrow diagram consecutive. So we have 1, 2, 3, 4. And 1 goes for the first time to 2, 2 goes to 3, and 3 goes to 4. And that same thing repeats itself for the second part, so the consecutive part. So 1 goes to 2, 2 goes to 3, and 3 goes to 4. And how many elements are in the composition? Then let's just try to get a line from the one on the left to the most set on the right. So we go from 1 to 2 and from 2 to 3. So that's 1. Yeah? So we have an ordered pair 1, 3. We go from 2 to 3, from 3 to 4. So the second one is 2, 4. Then from 3 to 4, and then we don't go anywhere. So the total number of elements is 2. It's only this set containing these 2 ordered pairs. And the last question of this exercise. So we have a few compositions. So we have R1 being the base one, R2 is the one we just made, R3 is one consecutive, etc. And then the question is there some element for which the composition, the total composition, is empty? Okay, let's just try it. So let's start with the first one we already made. We'll just repeat it. So 1, 2, 3, 4. 1, 2, 3, 4. This is the one we already had. And then the total one was this. I will not repeat all the black arrows. And so we had 2 elements left in R2. So on this spot here we have R2. Okay, then let's add another one. 1, 2, 3, 4. And then we can see that from 3 we can still go to 4, but 4 is out again. So this one here is R3, and it still has 1 element. Okay, we don't need to be Rockefeller to understand that if we continue one more, then there's nothing anymore. Huh? This is empty. There is no relation that gets us from the first set to the last set. So that means that R4, this one, R4, huh? the last step is empty. So, in fact, answer to the first one, is there an n for which R1 is empty? Yes. If so, give the smallest one. Well, it's this one. So, 4. And we don't need to explain any further. So, smallest one is 4. Question 5. We have a proposition. P implies Q implies P and Q. Give a proposition equivalent to this one in which only the operations and, or, and not are used, and you don't have to simplify. So the only thing they're asking us to do is get rid of this implication. Okay, how can we get rid of an implication? We'll use the switcheroo law. Switcheroo law 1. So we'll change the proposition into, so the first one changes in not P or Q. And then let's leave this one for now. So we've only changed this first part. Now let's do the second one again, also with the switcheroo law. So that means that this first complete part is negated, so not P or Q, or P and Q. And leave it, huh? We don't need to simplify, so we just got rid of the implications, and now we have only not, ors, and ands in our answer. Exercise B. Simplify as far as possible by using the logical laws. And the laws are given on the last sheet of the exam. So let's start. So first step, if we look at this proposition, we see a not and some things inside brackets. So let's first do the Morgan to simplify that part. So the proposition is equivalent with not P, or, and this or changes in and, the or switches, not Q, and for me you can immediately put that one is Q. So this complete first part is changed in not P and Q. And then we'll just copy what is left there. Okay, oh, that looks nice. We have a not P and a not P. We have an and, so next step is always look for similarities. And let's first check out the similarities in the operators. I have two ands, so I can use associative to drop the brackets at that point. So we have not P and Q and not P or Q. Okay, that's nice. Look, similarities again. I have a Q and a Q. So Q and not P or Q, that is absorption law. And remember, you can check out page 4 to see these laws if you don't see them fast enough. So Q and not P or Q will give us Q. Done. That's it. Not P and Q. I can't make it any simpler. So that's it. And then on question C, they ask us to make a truth table for a proposition. By the way, if we go back to this previous question, if you have plenty of time, my advice would be make a truth table for this one as well, and then check whether your answer is correct. That will give you some feeling of confidence. Okay, so for C, we're going to make a truth table. And thank God we only have two propositions, so I only need to make one with 4 combinations. So 1, 1, 0, 0, 1, 0, 1, 0. And then I have all the possibilities. Okay, let's start with the first one on the left, not P. So that would be 0, 0, 1, 1. And we go to the one on the right, and then the smallest part inside that one is Q and P. So that would give us 1, 0, 0, 0. Then we extend it a little bit. So we extend it with Q and P implies Q. Okay, Q and P implies Q. So there's a 1 here and a 1 there. That gives us a 1. And then, look, all the other Q and P's are 0. And if we start from a false, we get a truth in the implication. Lovely. Then we only have one step left, not P. So let's give this one a number 1. By implies the second one. So let's call this one 2. And then we have 1 by implies 2. So we have to check for similarities. So when is the by implication true? Only if the two columns we're checking for are the same values. So 0, 0, 1, 1. So apparently this complete proposition is just this basic truth value. Question 6. It's about a quantifier. So we have an existential one and a numerical one. And the question is the complete proposition true or false? Okay, let's try to read it. So can we find a y coming from z, so negative and positive whole numbers, in such a way that the number of elements coming from the natural numbers, so starting from 1, for which j, the second one is called j, for which j is smaller than the existential one, I, equals 3. So can I find a y which has 3 smaller numbers in the natural numbers? So if I would take y being 4, then if I find j's which are smaller than 4, that would be the set 1, 2, 3. And so if I is 4, then I can find 3 j's in such a way that they're smaller than 4. So yes, I can. I is true. And so most problematic on this exercise is that you have to be able to read what it says. And then it looks complicated, but just for your own, in your head, read it out loud, and then normally you will figure it out. Okay, this was part 2 of the exam. In the next video, we'll continue with exercise 7.